I will record. Okay.
So this presentation is about triboelectric energy harvesting interface, the project that was done by several members of the lab. So this presentation contains the motivation of the project and the proposed triboelectric nano generator interface. So the motivation. So what does it do? It basically turns mechanical energy that into high open circuit voltage. So in between this mechanical energy goes through a series of so this mechanical energy is turned into voltage due by a series by some circuit elements. So the energy extraction using TENG. So energy harvested when VT becomes is equal to Vrect. So as we can see in the graph, the VT is basically continuously changing to plus Vrect to minus Vrect, and then there is a small transition point that we can see in the red. So energy harvested only when VT is equal to Vrect. So therefore, during the time of phase change, power is not extracted. So and IT discharges the CT. CT is the charge of the capacitor that we can see here over here during the polarity change. So there is a wasted charge between this red region and also some wasted energy that we'll see. So energy wastage. So during this transition period, when the voltage is being voltage VT is transitioning from Vrect to minus Vrect, there is some phase change, and in this time of phase change, this power is basically wasted. So so power extraction, the power extraction is largely dependent on Vrect. So if you want to increase the energy extraction, we can always make the Vrect higher, because if we see the power is basically equal to the voltage times the average current. So for the same average current, for more Vrect, we will get more energy. But the problem is that in that case, we will have also more energy wastage. So there are issues with high Vrect. The first one, as we already saw, which is higher energy wastage. The second one is this marginal voltage, which is break. So the circuit is only capable of handling a certain amount of voltage, which we denote as V break, normally 70 volt. So if this, this actually significantly limits the VT. So as a result, it also limits the extracted power. So in order to address these two issues, the first proposed solution was to use dual output rectifier, as you can see over here. And this is the graph that the rectifier does. Basically, we're shortening the transition time over here. So the amount of power that is being wasted is actually shortened, but still it's not zero. And of course, the limit of the voltage, which is V break, the issue actually sustains. Another approach, which is basically a much better approach, was bias flip. So by flipping the bias, as we can see over here, the power wastage is actually almost minimalized, but the problem remains with the limited extraction voltage and restricted power. So the V break issue actually sustains. So in order to solve both issues simultaneously, we are going to use a multi-chip stackable technology. So multi-chip that will basically limitlessly extend the voltage limit, and also we can use the bias flip to eliminate the power wastage. So here is the proposed TENG in detail. So here it is. So multi-chip extract as well as stacked bias flip, as I've already said. So this is a master chip, and this is the slave chip, and these two chips can be connected in parallel or series. And depending on that, it will have different functionalities. When it is connected in a series, it will be used for high voltage harvesting. And when it is parallel, it will be used for bias flipping, bias flip. And we also have to switch between parallel and series in order to get both of the functionalities from the TENG. So here's the DC-DC converter that we're going to use in this multi-chip stacked bias flip. So how does the operation go on? So there are 4 phases in total. In phase 1, this is the phase 1 actually looks like this. We can see that certain switches are turned off, and certain switches are turned on. Switches are turned on. So in this case, the capacitors, both capacitors are actually connected in series, and the voltage is basically Vrect 1 plus Vrect 2. And the power extracted, if we calculate, is actually equal to 2 times the voltage direct. And this is the graph that we can see over here. In phase 2, these 2 chips are basically connected in parallel. So now this will work as bias flip. So bias flip, so as it is working as bias flip, this will now minimize the power wastage. And now the capacitors are also connected in parallel. And this is the bias flip is happened by the LC resonance. Phase 3 is basically same, but opposite of the phase 1. That means the switches that were turned off in phase 1 are now turned on, and vice versa. And the same calculations also applicable for phase 3. Phase 3 is actually the multi-chip stack that is used for increasing the limit of V break. And finally, the phase 4, which is similar to phase 2, the two chips are connected in parallel. The capacitors are also connected in parallel. The advantages of each technology is shown here. For the multi-chip stackable technology, so basically this is the advantage list of each of the technologies that has been used so far. Thank you so much. And that's the
Okay, thank you. You forgot to change the total number of slide, right?
Well, I couldn't do it. Like I tried.
You don't know how to do it?
No.
Okay, you are sharing my screen, right?
No.
I will share my screen. Will you share my screen?
Yeah, I can see.
You did not watch the video? Maybe the last meeting when I tell you how to change the slide, I did not record that part, right?
I don't think so. No.
So you go to view, okay? Slide matter. Okay. And then here you can change the number here.
Oh, okay.
Okay.
Okay, thank you.
View slide matter. When you want to come back, you go to normal. Okay.
Okay.
Yeah. Why you choose to review this? You make PT about this paper, right?
Yeah.
Why you choose to make this paper, not this paper? I think this paper is more basic.
I think I'll like time by time I'll also make paper on this. Like I'll help to make presentation on.
Sorry?
I will ultimately have to make presentation on this as well, so I will make it later.
Actually, this paper is more complex than this paper, I think.
Oh, okay. Actually, I didn't know that.
And did you read that paper?
No, I didn't read this paper.
You only this It's this slide, right?
Yeah, I only read this one.
Did you read your paper? Did you read the paper or only watch the slide? See the slide?
I just actually tried to read the paper, but I think thought that reading the slides should be like easier.
Yeah, right. But sometimes you need to look back the paper because the slide do not have the script here, so some part you need to read back your paper
I see.
for explanation more detail.
Hmm.
For you guys now is really difficult to read conference paper because you don't have much experience about your circuit. So for you guys, journal paper is easier to read, right? Normally, journal will be an extended version of the conference. For example, this GCICC, it is conference, International Solid State Solid State Circuit Conference. So it only have two or three pages. One page for text and 2 page for figures. However, they are the same work, right? The same, you figure here and you can see a journal. Here is a journal. They change a little bit in figure, but here is the same work. You can see the measurement. The same thing, right? Same measurement setup, right? Measurement here and measurement here. Journal is an extended version of conference by adding more than 40% information from your conference. So from your conference, you add more than 40% information from here plus 40 more percent. So you will add more figures and explanation to write a journal. So in journal, they will add more explain about the circuit in here. For example, this circuit, they will just briefly explain, but in journal, they will explain in more detail. So for you guys, if when you come to read the circuit level, you should find journals to read first. In the beginning, when you don't have experience. So can you send me the slide? I can ask some questions.
So my slide?
Yeah, you can. I think next time you should send slide first.
Okay.
Right. Before your meeting, you should send. You can email to this our email.
Okay. Video. I sent the
Okay, you. Mm.
Sorry.
Why here weighted chart is CT to be red?
Yeah, that's what's mentioned in the original slide. And,
It is correct. Weighted chart here.
I think, like, if you think about the full cycle, into
A whole entire cycle, then like it should be correct.
You mean here, right? In the red?
no. For the
Intercycle means from the left side, and from the entire left side to the
like entire complete wave cycle.
I'm talking about.
You mean one cycle is the chart, right?
Yeah.
This part. So for this part,
The wasted charge should be CT tends to be right.
But here they are weighting. Here not weighted. This chart will flow to capacitor.
Mm-hmm.
Actually, we are harvest. We will transfer chart to this cap. This cap is store
Okay.
energy. It's not weighted. Let's see.
Okay.
Let's see slide. P-rack is the power is transferred to this cap, right?
Mm-hmm.
CR cap. Power on the rectifier cap is equal voltage V-rack here to here between cap multiply average current. So the average current flow into the cap, right?
Mm-hmm.
IT mean this current, TENG current, and so some of current will flow. And for here you can see in this yellow color, right? Yellow color here. So that means in the yellow color,
the energy
this current will flow into rectifier. And in the transition, when the voltage change polarity, when current change polarity, in the transition, we are losing energy.
Yes.
So energy loss is between transition, right?
Mm-hmm.
So in here, you are wrong. Here not weighted. That is not weighted.
But in the
like original presentation says that it's
Chart CB. I think could be harvested. So the energy flow to this cap is harvested.
although like in the presentation it says that the energy is based.
Where?
Here,
Here?
the wasted charge.
Yeah, only weighted during this
Transition. Yeah, I'm also talking about the transition period in the slide as well.
You're right.
Yeah. So I'm also talking about this transition period in the slide as well.
Like I'm talking about when energy thing wasted during the polarity change.
Yeah, here. Where during the transition.
Mhm.
During the polarity change.
YCT. Do you know where this breakdown come from?
No, actually, I don't.
Actually, it come from the process. Do you know process? Fabricating process?
When during the process.
Yes, sir.
So, fabricating. I will briefly explain. Next time you should find more, right?
But like you should also like give us material we need to study so that we can study about the process.
Sorry?
Like where should we study? What is process?
You are started to study in your course. Yeah.
Like I need to study about process, right?
Yeah, your process.
Yeah. So like how should I study?
So process here 100 nano micrometer process mean your smallest so in here actually I'm using this process 100 nanometer process.
Oh, so everything like that.
Transistors have a size of 100 nanometer.
Right, smallest so you see here is in micrometer. Here should be millimeter 100. Yeah, in micrometer. So here is 0.22 micrometer. So the smallest part, smallest part in your layout is 100 micrometer.
Okay.
The smallest size in your layout. So because it is a smallest size, so if the process is smaller, mean you can make your chip smaller, right?
Mhm.
In smaller process, the size will be smaller. However, it will be more expensive. 100 here is 0.18 micrometer, 118 nanometer process is the cheap, the really cheap process. So for research, people normally use this process for the price, low price for research. And here is in VCD process, you can see the MOSFET 65. Actually, yeah, here 70. Here is the voltage, the target voltage. The MOSFET can work if the voltage over you. Did you know MOSFET will have gate, drain, and source, right?
Mm-hmm.
So 70 volt mean the gate, the voltage between drain and source, the largest voltage it can work. If it go over, 70 volt, the MOSFET will be broken. That is the breakdown voltage they are talking about here. So in this work, they try to stack two or more rectifier in to make the operating voltage is higher, right? So we can harvest more energy. That is the concept of this work. Do you know bias flip mean?
So the bias flip basically means that like the
Reversing the diodes, reversing the forward and reverse biases.
right?
Bias flip actually it means it will flip the voltage from positive to negative and opposite,
Okay.
right? It will flip the voltage. It is the main name for the bias flip. Actually, I have another slide for bias flip. Is Let me see. Actually, it originally come from piezoelectric energy harvesting, and they use the same way for triboelectric. Here the rectifier, right? The same. Energy loss in reverting in when the current change polarity and here they use an inductor to flip the voltage here quickly, right? In here without bias flip, so the voltage will slowly energy loss. So the current IP here will slowly charge this internal cap, right? In here on diode is off here, so the current will flow to this cap, and then the voltage in here will slowly change because they need time to charge this cap, right? However, when have inductor, the voltage will flip quickly because current will voltage will flow by the resonance from capacitor and inductor. Yeah, so it called bias flip. It is.
I see.
Yeah. RC resonance. So it will flip voltage. Next, we should I think in this paper, you can see the voltage is like sideways, right? Sideways. It's almost similar to piezoelectric. I think depends on your material of your tech, so your waveform could be different. So you can see in the paper it's like this. So it's not in sideways, right? Here's the voltage. So in the positive side will larger than negative side. So I think let's see. The model is. I want you to simulate the model and to check how to make so if in here if we apply a sideways current, so the voltage here also sideways, but I wonder how we can model the current with like this, if not in sideways, how to make it model.
By the way, like the meeting is almost gonna end, so should we rejoin?
Sorry.
Should we rejoin? Like the meeting is almost over.
Oh yeah, it's 1 minute left, so
But I think we can just like
Okay.
okay. Later I would think what we will do next week. Yeah, next week is okay now. So tomorrow I would think, yeah, I would think what we will do, and then I will tell you later. Okay.